What is going on, guys? My name is Hussein, and as some of you might know, I'm still in vacation and I don't have my regular office and mic and the camera, so I apologize for the audio quality. But I thought I'll make a quick video for the Q&A lecture of the month of December. I started doing this back in October, and you guys seem to enjoy this kind of interaction, right? Where I pick a question from the Introduction to Database Engineering Udemy course and elaborate on that. So, as you know, I almost answer every single question that you guys ask in the Udemy section, Q&A. But usually, when you type things and it's really hard to I am a verbal person. I like to talk more than I type, and my writing isn't that great to begin with. But I thought I'll just make a video to elaborate on one of these answers, and we'll pick one or two questions and elaborate on them. How about we start? So, I thought I'll start with this question from Shubham. Why will any update in Postgres updates all indexes corresponding to that table? Let's rephrase the question a little bit, right? And explain that what exactly is that, right? So this is referring to the must-watch video lecture, actually, of how tables and indexes are stored to this. I really, really recommend you watch this before really starting the course, because this is the fundamental things of building block that you need to understand and build upon yourself. Once you understand these basics, it's like understanding math. Once you understand how addition works, you know how multiplication will work. And once you understand how multiplication works, division just comes in naturally. Everything is derived from the thing that comes before it, right? You don't memorize, right? Things usually, like in math, you never memorize an equation. You know how it works and you derive it, right? You can solve anything by understanding the basic things. That's why we need to do the same thing with any domain. Really, engineering is one of them, right? We tend to memorize, we tend to say, oh, it's the way it is. Oh, MySQL or MongoDB is faster because it's just the way it is. No, it's just at the end of the day, it's just basic building things, building blocks. And once you understand these basic things, you don't need anyone, you don't need me anymore. You don't need anyone to tell you why is this better than this. You make the decision, because at the end of the day, you ask yourself, okay, why is this? Okay, how does this work? You know how it works, because at the end of the day, everything is IO, comes to databases. And we try to be smart in databases and start, okay, what is happening really, right? When you're issuing a SQL statement. Once you understand what is exactly is happening, you must go to another database and ask the same question. How is this database system doing compared to Postgres? How is MySQL doing compared to Postgres? Because at the end of the day, they have to solve a basic problem, right? How to optimize I/O. You're reading or writing to disk. You write it to memory. You have to flush to disk. You want to solve the durability problem. At the end of the day, it's all first principles that everybody need to adhere to. There is no exception. And the problem is marketing gets into the way. Oh, this is like in memory, whatever, all right? Or this is like faster, or this is on the cloud something. It just jargon gets into the way and gets confusing. So with that other way, let's get into the first question, which is, why will any update in Postgres updates indexes corresponding to that table? So this is something I mentioned in this lecture. And we really need to understand that indexes are there for a reason, right? Indexes are there so that we, right, avoid searching millions and millions and millions of things, whether these things are documents, rows, blobs, who cares, right? Indexes allow us to, take shortcuts. Think of an index like this. You're going to a secretary office. It says, oh, find me company Zebra, right? And there are a lot of, entries, right? Go find me the phone number of this company. It's called Zebra, right? You can take the phone book and search from A to Z, right? But an index says, okay, zebra starts with a Z. Let's only search the Z's, right? Or the Z's if you're from the UK. And that's basically what an index is. It just narrows the search space. It's like, oh, why are you searching A, B, C, D, no, all that stuff? Search only the things you need. That's exactly what an index does. It just smartly, based on the column that you indexed, builds a data structure, right, which needs to be stored, needs to be put in memory, needs to be IO'd. So you still need to manage this thing. It's not free. Nothing is free, right? So you build that data structure and you search it first. And then that data structure, that index will tell you, oh, go to this page and pull this row. It's there. It's 100% there. Or some indexes are, probabilistic. They tell you, I, it's definitely not there, but it may be there, and that's also a useful. It's called blue filters. Very, very useful stuff. So yeah, so once you understand that indexes are data structures that need to be stored, that need to be maintained, because the moment you update your heap, your source tables with data, you need to keep the index up to date, right? It's like adding a new, right, a new company phone number. You need to have the index, right, with the letter, have that point to the, the right entry. It's the same thing. Now comes the question. The question says, when you in Postgres, this is specifically in Postgres, and again, guys, don't get caught up with definitions or implementation details. Just understand how each database does stuff. It's just the way they chose to do this, right? Postgres, right, chose a specific design and they stuck with it. It has pros and cons, right? And I'm not going to tell you the pros and cons because you're going to figure it out yourself with logic. And the indexes, I said the indexes need to point back to the table, right? Which page and which row they need to read, right? And when you do that, what do we point to exactly? We need some sort of a identification of the row, right? This is what is called tuple ID in Postgres, at least, right? Every row you insert, it has a unique tuple ID, right? And if you update it in specifically in Postgres, you get a new tuple ID, right? But the row is the same logically. So to you, the reader, it's the same row, but it's in different tuple. Does that make sense? Right? So one logical row could have many, many tuple entries, and each tuple has a unique identifier. This unique identifier is what the index stores, and this is what effectively does the reading. All right, so where were we? We talked about having index data structures that are kind of separated from this large pool of raw data where the table exists, where the documents exist. And these are multiple indexes, because you can create an index on field A that will create a unique index data structure that will have X amount of bytes that will be stored in disk, that will need to be fetched, that will need to be put in memory, that will need to be queried, read, right? And you can have many, many, many of these indexes, right, based on your table, right? So let's say you have 3 indexes, each for each column. Column A have an index, column B have an index, column C has an index, right, which points back to the table. Now, this is a design choice that the Postgres team made. When you search an index, right, you found the value that you're looking for, the values with an S, right? Now, what does the value contain in the index, right? Because you're searching the keys of the index. The value, because it's a key value almost, right? Concept, right? The value of the element is basically the tuple ID that we talked about, right? Means that the tuple ID, this ephemeral thing that keeps changing, is stored on all the indexes. So now think about it. If I update my row, right, it's a unique row, and I made an update to a single field there. A new tuple ID will be created based on Postgres design. Again, this is only Postgres. Some other databases do a completely different design. So, and this is what I want you to keep an open mind. Is like, oh, this is not the way or the right way or the wrong way. This is just how it's done. You can come up with something to challenge any of the stuff that is being done today and completely revolutionize database engineering, right? And not in a fluffy way like we do it today, unfortunately. Everything's a fluff these days. Nothing is actually legit that is being discussed. So now, when I update my row, column A, right, what do we need to do? Right? First of all, we changed the content of column A. We didn't touch B or C, right? What happens in Postgres? Postgres creates an exact copy of that tuple, right? As a new tuple. You have a new tuple ID, brand new, right? But it's effectively, logically to you as a user, it's the same row. You just updated it, right? So now there is a new tuple ID. We updated field A, which has an index. B and C we didn't touch. But here's the problem. If you actually look in the index B and the index C, right, and the index A, all of them have entries which point to the old tuple, right? Because each tuple has a unique identifier. So all of these guys are pointing to the old one, right? So regardless of this, all the indexes need to know about this new tuple ID. I feel like I talked about this in another lecture. I apologize if I did, but I guess it doesn't hurt if I repeat it, right? So all these indexes need the knowledge of the new tuple ID, right? Because if someone starts searching, let's say, index C, which we didn't touch, right, for a value that points to that row, they will find the old tuple ID, and they will get the old value. Yeah, C wasn't touched, but what if they did select A from table where C equal blah? The blah was pointed to the old tuple ID, right? So now they will get the old value of A, not the one we updated. So regardless, we need to update those indexes, right, to have the new tuple ID, right? And that's technically a problem in Postgres, and that's why Uber complained. One of the reasons Uber complained about Postgres about this, right? Because now, hey, I updated column A. Why are you touching indexes B and C? So if you have a lot of indexes, right, then what you're gonna do is you will end up touching. And when I say touching, you're actually physically updating doing I/O, doing writes to these data structures. That's why I want you to think these are things that are not in the air. These needs to be maintained, and the maintenance of these is costly, right? So have you had a lot of these indexes, then it becomes a problem. But Postgres, I believe that's another question. Like invented something called the hot optimization, right? HOT, heap only tuple, and said, all right, we really didn't touch B or C. We only touched A. So does A have an index? If it doesn't have an index, we have to update index A, guys. You change the representation of the row for column A. There's an index on A. We need to let the index A have the new value of that row, right? Because the B tree has to be reshuffled, the B tree has to be updated, the keys have to be put into place. We need to do all of this stuff regardless. This is an update to the A field, which has an index. So you have to update the field A. But the performance optimization that the Postgres team did is like, what B and C shouldn't really need to be touched technically, right? Because they weren't touched, right? Why are you updating them? And that's what's called the hot optimization, which is right here. I don't know if you can see it from my face. It's right here, hot optimization, heap only tuple, which effectively keeps the old tuple ID in the index, right? But updates the heap table, which we're already doing because we updated the row, right? So that we do a pointer in the heap, that the old tuple ID actually points to the new tuple ID in the heap itself. So that if someone came to the old tuple ID, we let them know, hey, by the way, if you want the latest representation of this tuple, it has been updated. It's not it. There is a new one here. And this is done in the same page. Again, watch this lecture. Very important to watch this lecture to know what is the difference between a page and a row and all that jazz. Right? So the page has many rows, and each row has many tuples, at least in case of Postgres. So now you will have these multiple representations. So they inserted some metadata in the page that says, oh tuple ID blah is actually there is a new version of it. Go and jump to that. Some metadata. Keep in mind, only if the new updated tuple happened to be in the same page as the old tuple. Right? So what does that mean? Because a page has a fixed size. It's 8K in Postgres. It's 16K in MySQL. So the moment you update a row in Postgres, we create a new tuple ID. If there is a space left in the page, we're going to insert the new tuple ID in the page itself, which is this is the best thing you can do. Because now if I fetch the page, all the tuples I need is in this page. The moment you start jumping to another page, that's where you need more I/O. Again, it really depends about the disk size and the block sizes of the operating system, file systems. It's a little bit more complicated than that, but just think of it kind of logically, right? If things is in the same page, then it's more efficient, effectively. So a lot of DBAs configure something called the fill factor. How do you type this? Fill factor. Google that if you want to know more about it. And fill factor is a page configuration that says, okay, fill this page until 80%, fill this page until 50%. Right? When you create a new page, only fill it up until 50% and leave, what I understand is leave space for updates and deletes so that we can use it for later. But when you insert, fill it up until X amount of percentage, 80%, 70%, whatever you've configured, and then leave it empty. And then when you do that, what will happen is that page will leave some empty space in it for future updates, so that tuples that have been updated gets placed in the same page, right? They will be reused, and that's basically the power of fill factors. Very critical, very very critical configuration when you become a DBA. That's just one of the things you have to know, right? It's like and there's configuring this based on the workload is really something. Yeah, you get paid hand over fist for understanding these low level things, right? Configuring things. It really can break or make your architecture. All right, so that's basically it. So heap only tuple only works if the tuple is in the same page. If it's not in the same page, all bets are off. We gotta update the indexes regardless of what we're updating. So that's basically why we're updating this the indexes. And I guess this also answers this question, which is kind of similar. Someone had a similar question here, which is like I have some confusion regarding the hot approach for the right amplification problem, right? And I basically I just answered basically this kind of question as well. And so I guess I didn't talk about right amplification here. Right amplification is the idea of what we talked about. You do a single update as a user, right? There is a lecture called Right Amplification in this course, by the way, guys, check it out. So I did an update. I touched field A in the row. That's all I did as a user. Select, I did an update statement, and I just touched this thing. That's it. I just updated that single row. Didn't do anything. That only that column I touched it. But the right that you think you did have an amplification side effect because that's not really the only thing that you have done technically. There you have indexes in place, you have pages that need to be sorted and shuffled. If you have a clustered index, that's another story. There might be clustering that needs to be done. So there might be indexes that needs to be updated regardless of this RAM process. That those indexes might have a B-tree rebalancing, which will need more writes as a result, which results in an amplification of writes. So you're doing a single thing, but if you're looking at the I/O on disk, you see a flood of a lot of writes, right? Uber saw this specifically when they were doing replication, which I have a whole section on. They did a replication. They said, wait a second, why is the network bandwidth overflowing? Right, we didn't do anything. It's just a single update. They've seen a flood of writes, right? So that's when they say, okay, oh, we did another update, but we have 20 indexes that have been updated, right? And Postgres Uberware was on an old version of Postgres that didn't support heap only tuples, which is hot, which they saw all this amplification as a result. Postgres team tried to simplify the heap only tuple problem. The amplification by doing the hot optimization. They did many other optimizations as well. All right, guys, that's it for me today. I'm going to see you on the next one. Hope you enjoyed this lecture. Talk to you later. Goodbye.